On December 14th, Eugene Cernan became the last human being to walk on the moon. He stood in the Taurus Littrow Valley, looked back at the lunar module, and said goodbye. We went to the moon 6 times. 12 men walked on its surface and brought back hundreds of kilograms of lunar rock. And then it ended. Not because we failed. It ended because the conditions that made it possible vanished. The moon landings weren't the beginning of a new age of exploration. They were the final act of a very specific moment in history. When that moment passed, space didn't become easier. It got harder after we reached the moon. The end began almost as soon as the beginning was complete. NASA's budget peaked in 1965, 4 years before the moon landing. After that, it began to decline. By 1970, NASA's budget had dropped to 2.5% of federal spending. By 1975, it was below 1%, and it has remained at or below 1% ever since. This wasn't just a matter of shifting priorities. It was a fundamental change in how America viewed government-led technological programs. The political consensus that supported Apollo evaporated for several reasons. First, the space race was over. Once American astronauts reached the moon in 1969, the symbolic victory was achieved. The Soviet Union never developed a competitive lunar program. Nikita Khrushchev was never fully committed to a moon landing and focused on missiles instead. When Sergei Korolev, the chief architect of the Soviet space program, died in 1966, their lunar efforts effectively ended. Second, domestic priorities shifted. By 1970, America was deep into the Vietnam War. The economy was slowing, inflation was rising, social programs demanded funding. The moon seemed less urgent when cities were burning and young Americans were dying overseas. President Richard Nixon, who took office in 1969, explicitly redefined space as just another domestic program competing for limited resources. Third, public support was never as strong as we remember. 45% and 60% of Americans believed the government was spending too much on space. Only briefly, in 1969, did a majority support the program. The perception that everyone loved Apollo is a myth. It was controversial, expensive, and politically vulnerable from the start. And fourth, institutional momentum vanished. NASA was built to achieve a single objective: land on the moon before 1970. Once that objective was met, the agency had no clear mission. The Space Task Group, formed by Nixon to plan NASA's future, proposed 3 ambitious options ranging from a Mars mission to lunar bases to space stations. Nixon chose none of them. Instead, in January 1972, he authorized only the Space Transportation System, the Space Shuttle. And even that came with severe budget constraints. The shuttle was supposed to be fully reusable, flying frequently with low costs. But funding limitations forced compromises in the design. The solid rocket boosters were made reusable, but required extensive refurbishment. The external tank was expendable. The orbiter's heat tiles needed individual inspection after every flight. The shuttle never achieved its promised economics. Each flight cost approximately $450 million, far more than originally estimated. More critically, the shuttle couldn't go beyond low Earth orbit. It was designed for orbital missions, only deploying satellites, conducting experiments, building the International Space Station. The moon was off the table. When Apollo ended, we lost more than just missions. The Saturn V rocket, the most powerful launch vehicle ever built, stopped production in 1973. This wasn't just about hardware, it was about institutional memory. NASA documented everything during Apollo. Manuals, procedures, test data, design specifications, all of it was preserved. But documentation alone isn't enough to recreate complex systems. Building a Saturn V required thousands of tacit knowledge holders. Engineers who understood the subtle quirks of welds, machinists who knew how to handle specialized alloys, technicians who could troubleshoot one-of-a-kind systems. When those people left, that knowledge left with them. Today, If NASA wanted to rebuild a Saturn V, they couldn't. Not because the blueprints are missing, but because the industrial ecosystem that supported it no longer exists. The same is true for other Apollo systems. The F1 engine that powered the Saturn V's first stage was a masterpiece of engineering. Rocketdyne, the company that built it, conducted extensive testing to refine its design. But much of that testing was done through trial and error, with engineers making adjustments based on experience rather than formalized processes. NASA attempted to reverse engineer the F1. They scanned original engines and studied the documentation, but they encountered problems that weren't recorded anywhere. Manufacturing tolerances that existed only in the hands of the original machinists. Material treatments that were standard practice but never written down. Welding techniques that were passed along verbally. The agency concluded that it would be easier to design a new engine than to exactly recreate the F1. This pattern repeated across Apollo systems. The Apollo guidance computer, the lunar module, the spacesuits, all of them were products of a specific time, built by a specific workforce, using specific processes that are difficult or impossible to replicate today. And beyond hardware, NASA lost institutional culture. Apollo operated with an unusual degree of autonomy and risk tolerance. Administrator James Webb protected the program from political interference. Engineers were empowered to make rapid decisions. Failures were treated as learning opportunities rather than career-ending disasters. This culture was born from Cold War urgency. It thrived in an environment where speed mattered more than caution, and it died when that urgency disappeared. After Apollo, NASA became more bureaucratic. Safety reviews expanded, oversight increased, decision-making slowed. Some of this was necessary. The Apollo 1 fire in 1967 killed 3 astronauts during a ground test. The Challenger disaster in 1986 killed 7 during launch. The Columbia disaster in 2003 killed 7 during re-entry. These tragedies forced NASA to prioritize safety, and rightly so. But the result was a more risk-averse organization, one that moves cautiously and requires extensive justification before attempting anything bold. This shift had consequences. After Apollo, NASA's ambitions shrank. The shuttle flew to low Earth orbit. The International Space Station orbited at 250 miles altitude. Mars rovers landed on the red planet, but no humans followed. The moon remained out of reach. Not because we lacked the technology, but because we lacked the political will, the institutional structure, and the cultural momentum to go back. For 30 years after Apollo ended, America's human spaceflight program focused on the Space Shuttle. The shuttle was supposed to revolutionize space access. NASA promised it would fly every 2 weeks, dramatically reducing the cost of reaching orbit. It would be reusable, reliable, and routine, more like an airplane than a rocket. It didn't work out that way. The shuttle first flew in 1981. Over the next 3 decades, it flew 135 missions, but it never achieved the promised flight rate. The most launches in a single year was 9 in 1985. On average, the shuttle flew 5 to 6 times per year, and it wasn't cheap. Each shuttle mission cost approximately $450 million, or about $1.5 billion when accounting for development costs spread across the program. This was far more expensive than expendable rockets that could deliver similar payloads to orbit. The shuttle was also dangerous. 2 of the 5 orbiters were lost in catastrophic failures. Challenger exploded 73 seconds after launch in 1986, killing all 7 crew members. Columbia disintegrated during re-entry in 2003, killing another 7. These disasters exposed fundamental design flaws. Unlike Apollo's Saturn V, which placed the crew capsule at the top of the rocket, the shuttle positioned the orbiter alongside the external tank and solid rocket boosters. This configuration made the crew vulnerable to debris strikes during launch, exactly what caused the Columbia disaster. The shuttle also lacked a launch escape system. If something went wrong during ascent, The crew had no way to abort. They either rode the problem out or died. These compromises were made to save money. NASA's budget in the 1,970 seconds couldn't support the fully reusable design originally envisioned. Engineers had to make trade-offs, and safety suffered. But the bigger issue was strategic. The shuttle was designed to do everything: deploy satellites, conduct experiments, build space stations, service the Hubble Space Telescope, and even carry military payloads. This flexibility came at a cost. The orbiter was complex, expensive, and difficult to maintain. And critically, the shuttle couldn't go beyond low Earth orbit. It was optimized for short-duration missions at altitudes between 200 and 400 miles. Reaching the moon would have required a fundamentally different vehicle. So for 30 years, America's astronauts circled the Earth. They did important work building the International Space Station, conducting scientific research, training for long-duration missions. But they went nowhere beyond where Mercury and Gemini had gone decades earlier. The moon remained a memory. The shuttle retired in 2011, and for the next 9 years, America had no way to launch its own astronauts. We relied on Russian Soyuz capsules to reach the space station. This gap was finally closed in 2020, when SpaceX's Crew Dragon began flying astronauts to orbit. But even now, we're still operating in low Earth orbit. The moon is farther away than it's been in 50 years. Apollo moved fast because it faced almost no external obstacles. Environmental reviews didn't exist. NASA could test rocket engines, build launch facilities, and conduct operations with minimal regulatory oversight. When problems arose, the agency fixed them internally and moved forward. That world no longer exists. Today, launching a rocket requires navigating a complex web of federal, state, and local regulations. The Federal Aviation Administration oversees launch licensing. The Environmental Protection Agency reviews environmental impacts. The Fish and Wildlife Service evaluates effects on protected species. State agencies add their own requirements. Each of these reviews takes time. Consider the recent experience with SpaceX's Starship development in Texas. The company built a launch facility at Boca Chica, near Brownsville. Before conducting test flights, SpaceX had to complete an environmental assessment that examined noise impacts, wildlife disruption, water usage, and debris risks. The first environmental review took over a year. Subsequent reviews added months to the testing timeline, and this isn't unique to SpaceX. Every launch provider faces similar delays. NASA's own Space Launch System, the rocket designed to return astronauts to the moon, has encountered repeated delays due to regulatory and administrative processes. Between design reviews, safety assessments, and environmental evaluations, the timeline has stretched from an original target of 2017 to actual first flight in 2022. None of this is inherently bad. Environmental protections matter. Safety reviews save lives. Public input has value, but the cumulative effect is a dramatic slowdown in the pace of space exploration. In the 1,960 seconds, NASA went from Kennedy's speech to lunar landing in 8 years. Today, developing a new human-rated spacecraft takes a decade or more. Part of this is due to technical complexity. Modern spacecraft are more sophisticated than Apollo-era vehicles. They have advanced computers, life support systems, and safety features that didn't exist in the 1,960 seconds. But much of the delay comes from process. Every decision requires multiple layers of approval. Every design change triggers reviews. Every test must be documented, analyzed, and justified. NASA's bureaucracy has grown alongside these requirements. The agency now has offices dedicated to safety and mission assurance, environmental compliance, procurement oversight, and stakeholder engagement. These offices perform important functions, but they also slow everything down. This creates a paradox. Modern space programs are safer and more carefully planned than Apollo, but they're also slower and more expensive. And in some ways, they're less innovative. Apollo thrived on rapid iteration. Engineers tested ideas, learned from failures, and implemented fixes quickly. The culture rewarded bold decisions and tolerated risk. Today's risk-averse environment makes that approach difficult. Failures trigger investigations, budget reviews, and political scrutiny. Programs can be cancelled after a single setback. Managers prioritize avoiding problems over solving them. This isn't a criticism of any individual or organization. It's a description of how the system has evolved. The regulatory framework designed to prevent disasters also prevents progress. Money is the most obvious constraint on space exploration, and the numbers tell a clear story. At Apollo's peak in 1965, NASA received $5.2 billion, representing 5.3% of the federal budget. In 2024, NASA's budget is approximately $25 billion. That sounds like a massive increase. But adjusted for inflation, NASA's budget today is roughly equivalent to what it was in the late 1970s. And as a percentage of federal spending, it's less than 1/5 what it was during Apollo. If NASA received the same share of the federal budget today as it did in 1965, its annual budget would be over $200 billion. Instead, it gets $25 billion. This forces difficult choices. NASA must balance human spaceflight with robotic missions, Earth science, astrophysics, planetary science, and aeronautics research. Each of these areas competes for limited funds. The Artemis program, NASA's current effort to return to the Moon, has a projected cost of approximately $93 billion through 2025. That includes the Space Launch System rocket, the Orion spacecraft, lunar landers, spacesuits, and supporting infrastructure. By comparison, Apollo cost $257 billion in inflation-adjusted dollars. So Artemis is cheaper, but it's also moving slower. The first Artemis lunar landing is currently scheduled for 2026, 5 years after the program's initial 2024 target. And that timeline assumes no further delays. These delays aren't just technical, they're financial. When NASA's budget doesn't increase with inflation, programs stretch out, development slows, launches get postponed, contractors reduce staff. This creates a vicious cycle. Longer timelines increase costs. Higher costs consume more budget. Less budget remains for other priorities. Congress tries to manage this by micromanaging NASA's spending. Appropriations bills specify exactly which programs receive funding and how much. This prevents NASA from reallocating resources to respond to changing circumstances. The result is inefficiency. Money gets spent on programs that no longer make sense, simply because Congress mandated it. Meanwhile, promising initiatives struggle for funding because they weren't included in budget projections made years earlier. This is fundamentally different from Apollo. During Apollo, NASA had flexibility. Administrator James Webb could shift resources between projects. Contractors could accelerate work when needed. The agency responded to problems with money rather than committee meetings. Today's NASA can't do that. Every dollar is accounted for. Every expenditure requires justification. The budget is a constraint, not a tool. And there's a deeper issue: competing priorities. In the 1960 seconds, going to the Moon was America's technological priority. Other programs mattered, but Apollo came first. Today, space competes with artificial intelligence, quantum computing, biotechnology, climate technology, and countless other fields for attention and resources. The Moon is important, but it's not the national imperative it once was. This makes sustained funding difficult. Presidents propose ambitious space programs. Congress provides initial funding. Then priorities shift, budgets tighten, and the programs languish. It's happened repeatedly since Apollo ended. President George H.W. Bush proposed a Mars mission in 1989. It was never funded. President George W. Bush proposed returning to the Moon in 2004 through the Constellation program. It was cancelled in 2010. President Obama redirected focus toward asteroids and eventually Mars. That plan faded. President Trump initiated Artemis in 2019. It continues, but faces constant budget uncertainty. Without consistent, long-term funding, programs can't succeed. And without political consensus, long-term funding doesn't happen. This is why space got harder after Apollo. Not because the engineering became more difficult, but because the political and financial support disappeared. Something changed in the 2000s. For decades after Apollo, NASA maintained a near monopoly on American human spaceflight. The agency designed spacecraft, selected contractors, and controlled every aspect of missions. Then, private companies entered the picture. SpaceX was founded in 2002 with the goal of reducing space transportation costs. The company developed the Falcon 9 rocket, which became the first orbital-class booster to successfully land and fly again. This was revolutionary. Reusability had been NASA's goal with the Space Shuttle, but the shuttle never achieved true reusability. It required months of refurbishment between flights. Falcon 9 boosters land themselves and can fly again within weeks. Some have flown more than 20 times. The cost savings are dramatic. SpaceX can launch payloads to orbit for approximately $60 million per flight. That's roughly 1/3 the cost of traditional expendable rockets. But the real breakthrough wasn't technical. It was contractual. NASA's Commercial Crew Program, initiated in 2010, used a fundamentally different approach than Apollo. Instead of specifying every detail of spacecraft design, NASA established performance requirements and allowed companies to propose solutions. SpaceX and Boeing competed for contracts. Both received funding to develop crew capsules, but they retained ownership of their vehicles and could sell flights to other customers. This created market incentives. Companies succeeded by delivering capability efficiently. Those that couldn't compete failed. The government paid only for results, not for development costs. The outcome vindicated the approach. SpaceX developed Crew Dragon for approximately $2.6 billion. NASA estimates that using traditional contracting methods would have cost taxpayers between $20 and $30 billion for equivalent capability. That's an order of magnitude difference. Boeing's Starliner has faced more challenges, but the company absorbed the cost overruns rather than passing them to taxpayers. This model has expanded beyond crew vehicles. NASA's Commercial Lunar Payload Services program uses similar methods to deliver cargo to the moon. Multiple companies compete for contracts. They develop landers using private capital. NASA pays only for successful deliveries. And the Artemis program leverages this approach for the human landing system. SpaceX won the initial contract to develop Starship, a fully reusable spacecraft designed to carry astronauts from lunar orbit to the surface. Starship is being developed primarily with SpaceX's own funding. NASA's contribution is relatively modest compared to Apollo-era spending. This shift has profound implications. If commercial companies can develop lunar transportation systems, NASA can focus on other challenges: life support, habitat construction, scientific equipment, mission operations. The agency becomes a coordinator rather than a builder, and that might be more efficient. But there are risks. Commercial companies answer to shareholders, not Congress. If a lunar program isn't profitable, they might abandon it. And private companies lack the long-term perspective that government programs can maintain. SpaceX is betting on Starship becoming profitable through satellite deployment and point-to-point Earth transportation. The lunar market is secondary. What happens if that bet fails? This uncertainty is part of the new reality. Space exploration is no longer solely a government endeavor. It's a hybrid ecosystem of public agencies and private firms, each with different motivations and constraints. This could make returning to the moon easier, or it could introduce new complications we haven't anticipated. We'll find out soon. NASA's Artemis program aims to return astronauts to the moon by 2026. If successful, it will mark the first crewed lunar landing in over 50 years. But Artemis faces challenges that Apollo never encountered. The program architecture is complex. Unlike Apollo's streamlined approach, a single massive rocket carrying everything needed for the mission, Artemis requires multiple launches and in-orbit assembly. Here's how it works. The Space Launch System rocket will launch the Orion spacecraft with astronauts aboard. Orion will travel to lunar orbit and dock with the Gateway, a small space station orbiting the Moon. Separately, SpaceX's Starship will launch to Earth orbit. A series of tanker Starships will launch, one after another, to refuel the first Starship through on-orbit propellant transfer. Once fueled, Starship will travel to lunar orbit and dock with Gateway. Astronauts will transfer from Orion to Starship. Starship will descend to the lunar surface. After surface operations, Starship will return to Gateway. Astronauts will transfer back to Orion for the journey home. This requires at least many successful launches for a single lunar mission. Compare that to Apollo, which required just one Saturn V launch per mission. Every additional launch adds risk. Every docking maneuver introduces potential failure modes, and the entire architecture depends on successfully demonstrating in orbit, refueling something that has never been done with cryogenic propellants at this scale. Then there's the timeline. The Space Launch System has flown once on the uncrewed Artemis I mission in November 2022. Artemis II, the first crewed flight around the Moon, is scheduled for 2025. Artemis III, the lunar landing mission, is planned for 2026, but delays are likely. Orion's heat shield experienced unexpected erosion during Artemis Avern's re-entry. The issue must be understood and corrected before flying with crew. SpaceX's Starship is still in development, with test flights ongoing. Gateway's first modules won't launch until 2025 at the earliest. Any problem in any of these elements delays the entire program. And there are broader concerns. Artemis is expensive. The program costs billions per year. Some of that spending is justified. Developing new capabilities requires investment. But some critics argue the architecture is unnecessarily complex and that NASA should use commercial systems more extensively. There's also political risk. Artemis was initiated by the Trump administration, continued by the Biden administration. But will future administrations maintain support? Every presidential transition creates uncertainty. Programs get reviewed. Priorities shift. What seems essential to one administration might seem expendable to another. This happened with Constellation, the previous lunar program, which was cancelled after one administration change. Artemis has bipartisan support in Congress, but that support is contingent on the program making progress. Extended delays or cost overruns could erode political backing, and even if Artemis succeeds, it's only the beginning. NASA wants to establish a sustained lunar presence, not just flags and footprints, but permanent infrastructure, habitats, power systems, mining equipment, manufacturing facilities. That will require far more funding than a few initial landings. The question is whether America has the patience and commitment to see it through. Apollo succeeded because it had a clear finish line: land on the Moon before 1970. Once that was achieved, the program ended. Artemis has no such endpoint. It's designed to be ongoing, indefinite, and expanding. That makes it fundamentally different and potentially more vulnerable to the political and economic forces that ended Apollo. So why did space get harder after we reached the Moon? It's not one reason. It's many, layered and interconnected. The political consensus that made Apollo possible dissolved. The Cold War rationale disappeared. Public support, which was never overwhelming, faded entirely. Presidents and Congress lost interest as other crises demanded attention. The budget that funded Apollo evaporated. NASA's share of federal spending dropped by 80%. Without sustained funding, programs stretched out, costs increased, and ambitions shrank. The regulatory environment transformed. What was once possible with minimal oversight now requires years of environmental reviews, safety assessments, and stakeholder consultations. This makes everything slower and more expensive. The institutional knowledge built during Apollo dispersed, engineers retired, factories closed, supply chains dissolved. the tacit knowledge that made rapid development possible was lost. The cultural tolerance for risk declined. After multiple disasters, NASA became more cautious. Safety reviews expanded. Decision-making slowed. The bold, fast-moving spirit of Apollo gave way to bureaucratic caution. And the very success of Apollo created unrealistic expectations. We assume that because we did it once, we can do it again easily. But Apollo succeeded because of unique circumstances that haven't repeated. All of this means that returning to the moon is harder now than it was in the 1,960 seconds. Not technically harder. In many ways, we have better technology than Apollo did. Our rockets are more reliable. Our computers are immeasurably more powerful. Our understanding of the lunar environment is far deeper. But systemically, institutionally, politically, it's harder. We can't simply rebuild Apollo. The world that made Apollo possible no longer exists. Instead, we have to find a new path, one that works with today's constraints, one that leverages commercial partnerships, one that maintains political support despite budget limitations and competing priorities. Artemis represents that attempt. It's slower than Apollo, more complex, and less certain, but it's adapted to modern realities. Whether it succeeds depends not just on engineering, but on whether America can sustain commitment to an objective that offers no clear geopolitical advantage, no imminent threat to motivate urgency, and no obvious economic return. Apollo had all of those things. Artemis has none of them. And yet, we're trying. Because some things are worth doing not because they're easy, but because they're hard. Because they challenge us. Because they represent human ambition to explore, to learn, to expand beyond the boundaries we've known. Eugene Cernan left the last footprints on the moon in 1972. If Artemis succeeds, new footprints will appear in 2026. And unlike Apollo, they won't be the last. They'll be the first of many, the beginning of something permanent. That's the goal, anyway. Whether we achieve it depends on lessons learned from 50 years of absence. We left the moon once. Coming back has taken decades. Staying there will require everything we've learned along the way about commitment, patience, and the true cost of exploration. Space didn't get harder because the moon moved farther away. It got harder because we did. We solved the engineering challenges of reaching another world, but we haven't solved the human challenges of staying there. Perhaps that's the real lesson of Apollo. The hardest part isn't the journey, it's the commitment to keep going. For now, we watch, we build, we prepare, and we hope that this time, when we return to the moon, we won't leave quite so soon.